Let's investigate another right triangle that lives in the unit circle. First, we're going to have a look at an equilateral triangle, and we're going to use that equilateral triangle to construct the triangle of interest. So this is the equilateral triangle. And this particular equilateral triangle has side lengths of 1. So this is 1, and this is 1. All three angles in the equilateral triangle have a value of 60 degrees. And 60 degrees is the same as pi on 3 radians. You can think of pi radians as being half a rotation around the circle. So you're going half a circle around, and that is a full pi rotation. And if you want to go pi on 3, that is just a third of a half circle rotation. So that is the same as 60 degrees, because pi radians is 180 degrees, and pi on 3 radians is 60 degrees. And 60 times 3 is 180. That's the same relationship between pi on 3 and pi. So it's just a third. And that's what this little extension of the diagram shows over here. So that is why pi on 3 is the angle for all of these guys. But here's what we're going to do. We're going to take a vertical line and we're going to slice this equilateral triangle in half. So this left-hand side is what we're going to be focusing on. But let's keep looking at this picture for just a few more seconds. This angle over here is pi on 6. And pi on 6 is half of pi on 3. So this is the same as 60 degrees, and this is the same as 30 degrees. You're taking 60 degrees and you're splitting it into 2 even chunks. So that's 30 and 30. So that's pi on 6 and pi on 6 in radians. And this triangle is sometimes referred to as the 30, 60, 90 triangle. It's just referring to all of the angles in that triangle. So I'll write that up over here. The 30, 60, 90 triangle. That's what this one is over here. So we got 2 copies of that. And the 30, 60, 90 triangle is just 1/2 of an equilateral triangle. So we've just split that equilateral triangle into 2 of these special triangles. And the special thing about this triangle is that this angle is twice the size of this angle, and that this angle is 90 degrees. So we still have a right angled triangle. There is a perpendicular angle over here. That's because this line that came down is a perpendicular bisector. It's a perpendicular bisector because it cut this into 2 even chunks. And because this entire side length is equal to 1, by definition, we've defined this equilateral triangle to have all of its sides equal to 1. We know that if we split it into 2 even chunks, that's going to give us 1/2 and 1/2. Now, let's zoom in onto just this left triangle. So just this left 30, 60, 90 triangle. Over here we have 60 degrees, which is pi on 3 radians. And over here we have 30 degrees, which is pi on 6 radians. We know that this is 1. So the hypotenuse of this triangle is equal to 1. And this side down here is equal to 1/2. So that has all come from this diagram over here. The equilateral triangle has been used to construct this triangle. The only thing that we don't know is the length of this side over here. So I'm going to call that y. And we're going to solve for y using Pythagoras Theorem. So this is the hypotenuse, and these are the other 2 sides in a right angled triangle. So let's write down Pythagoras Theorem. So Pythagoras Theorem is going to tell us that if we square this guy and add it to the square of this guy, that we have to be equal to the square of the hypotenuse. So if we take 1/2 and we square that, and then we add to that y squared, that should be equal to 1 squared. And 1 squared is equal to 1. So this is the hypotenuse squared. So let's simplify this side. We have 1/4, because 1/2 of a half is a quarter. And this is just going to be y squared, and this is going to be equal to 1. So now what we want to do is we want to subtract a quarter from both sides. That's going to give us y squared is equal to 1 minus a quarter. Now what's 1 minus a quarter? Well, 1 is the same as 4 quarters. So this is just taking one of those quarters away, and that's going to leave 3 quarters. So we're going to have y squared is the same as 4 over 4 minus 1 over 4, and that's just going to leave 3 over 4. So we have 3 over 4 because we've just taken 1/4 away from those 4 quarters. So this is a whole, and this is 1/4, and we're left with 3 quarters. Now let's take the square root of both sides to isolate y. So y is going to be equal to the square root of 3 over 4. But have a look at this. We're only considering the positive solution. We don't really care about the negative solution because this is a positive length. We're only interested in the positive solution when we take the square root, because the negative solution doesn't have a geometric visual intuition over here. So now what we're going to do is we're actually going to simplify this a little bit further. 4 we can identify is a perfect square. 4 is the square of 2. So this is the same as root 3 over 2. So we've just simplified the square root of 4, we've evaluated that, and we've made it into 2. There is no way to simplify the square root of 3. The square root of 3 is an irrational number. So we can't actually make this any simpler. So let's write this down over here. We have the square root of 3 divided by 2. And you could actually create an alternative triangle that is twice as big as this one. You could multiply all of the sides by 2. That would still preserve all of the angles. It would still be a 30, 60, 90 triangle. And sometimes that is actually what is shown. Sometimes you can actually multiply all these guys by 2. That would give you a 2 for the hypotenuse, a 1 down over here, and it would get rid of this factor of a half over here and would just leave root 3. But I've specifically chosen the hypotenuse to be of length 1, because what we want to do is we want to take this triangle and we want to put it inside the unit circle. This is the top right quadrant of the unit circle. And what I've done is I've actually put this triangle inside. And I've also taken this triangle, reflected it, and put it on its long side over here. So we have 2 versions of the same triangle. This is the 30, 60, 90 triangle. In this version over here, where its long side is along the horizontal axis, we have the angle pi on 6. So this is the same as 30 degrees. So pi on 6 is half of pi on 3. And this full angle over here, this is pi on 3. So I'm going to write that over here. So this actually corresponds to pi on 3 radians, which is 60 degrees. And this corresponds to pi on 6 radians, which is 30 degrees. And both of these lines that come down are perpendicular to the horizontal axis. That is why we have a right angle over here. And we know, because all of the angles in a triangle have to add up to 180 degrees, we know that these guys are actually the complements of each other. So this is pi on 6 up here, and this is pi on 3 up here. So we know that both of these triangles have to be 30, 60, 90 triangles. You just have to take this guy and put it up here. You have to take this guy and put it over here. So that's what happens when you're the complement of each other. So 30 and 60 are the complement of each other when we're looking at 90 degrees. And the other 90 degrees is taken care of by this angle. So then we have 90 plus 90, which adds up to 180 degrees. And that is exactly what we need in a flat space. In a Euclidean geometry, you have to have all of the angles in a triangle add up to 180 degrees. So now let's write down the coordinates over here. So the coordinates are actually going to be given by these side lengths. So let's have a look at the pi on 6 case over here. So this is the shorter side. This is 1/2. So we can actually write that as the vertical component. And the horizontal component is going to be this y over here, which is root 3 on 2. So I'll write that next to this guy over here. So the horizontal component is root 3 on 2, and the vertical component is 1/2. Now let's do the same for this guy. They're just going to be flipped. So this is going to be 1/2, and this is going to be root 3 on 2. So you can see that these are the same values, they're just flipped over, because the triangle is just flipped over. We're just flipping that triangle over, and we're swapping the vertical and horizontal components. But we're still keeping the angles in the triangle the same. We're just swapping their position in the diagram. So what does this actually tell us? This tells us the cosine and sine values evaluated at these 2 angles. So this first component is the horizontal component, and the horizontal component corresponds to cosine. And this second component is the vertical component, and the vertical component corresponds to sine. So I'm going to write that down. What we have is actually 4 very important answers to trigonometric problems in this diagram. So if we take the cosine of pi on 6, which is 30 degrees, that's going to be equal to root 3 on 2. This is root 3 on 2. And if we take the sine of pi on 6, which is 30 degrees, that is going to be equal to 1/2. So sine of 30 degrees is equal to 1/2. Now let's do the other 2. We have the cosine of pi on 3 and the sine of pi on 3. And what's going to happen, we're actually just going to swap these guys over. So the cosine of pi on 3 That's this guy over here. That is the horizontal distance. That is 1/2. This is 1/2, and this is 1/2. So this is 1/2, and you can see that the other guy has to be √3 on 2. And why is that the case? Well, sine of pi on 3, that is this height. The height from here to here. That is the sine of 60 degrees. And that is equal to this distance over here, √3 on 2, because that's the longest side over here that we have, √3 on 2. So we've actually derived all of these guys. And we can also work out the tan. And we're going to do that in a separate video that is dedicated just to the tan of all of these angles. So this video has given us a lot of information about what happens for 30 degrees and for 60 degrees. And in the previous video, we worked out all the information we need for 45 degrees. And these are three very important angles: 30 degrees, 45 degrees, and 60 degrees. We're going to keep talking about these angles in the next upcoming videos about the unit circle. Why is this important? Well, it's because the unit circle is intrinsically linked to the complex plane as well. So we're doing a lot of this geometry and a lot of this algebra, and we're linking that to the complex plane. And the complex plane is very useful in quantum mechanics and in other physics applications. That's why this is in the quantum mechanics playlist. If you want to find the other videos also about similar topics where we discuss these very useful mathematical ideas, you can find all of those videos in the quantum mechanics playlist if you click over